Goss. Okay, so this lecture, we're going to find something called the electric flux. So, I'm going to draw, say, a point charge. We've got these electric field lines. They look something like this. And what we're going to do in this lecture, we're going to define something called electric flux. And I'm not going to really motivate that, like why we're doing this. It's going to, the next lecture, we're going to talk about like why this is such a useful concept. So right now, we're just defining something, so you kind of just have to go along with it, and just know that it will be something very useful later. So this is going to be a short lecture because we're just defining something. Okay. So these electric field lines are spreading out, and this is like a spherical distribution. Like these lines are spreading out in a spherical pattern. Now, if you go far away, the electric field lines are going to be more or less parallel to each other. All right, again, so we have to picture this is farther away than it looks. Like, I don't have enough room to expand it. So again, if we look at like this point here, it should be going in a line directly away from this charge, so it'd actually be going like in that direction. And this point here would be going in that direction. But if we increase the distance, these angles get closer and closer to being parallel. So if we go far enough away, we can say that these lines are basically parallel to each other. And there's other ways of creating a sequence of, parallel electric field lines, but for now, we're going to just go with this. Just say we're far away from a point charge. And we're doing this because it's actually easier than considering these electric field lines that are going in various directions. So what we're going to do is we're going to draw a surface here that has an area A. And what we want is basically a measure of how many of these electric field lines are passing through this surface. Now, the key word there is passing through this surface. And so I'm going to start out, in this case, it's we're going to find the flux. We use this letter, it's a Greek letter phi. And for now, I'm just going to say it's the electric field times the area. So yeah, we're intuitively thinking of it as kind of like a measure of how many lines are passing through this surface. And so if we have like a bigger surface, we'd get more lines. If you double the surface, you'd get double the flux, twice as many lines through it. Also, if we have a stronger electric field, then we would have more electric field lines. So again, this is just how we're defining flux. However, this is kind of a simplified case, because what if we turn our surface? What if we have our surface going at an angle? And instead of turning the surface, what I actually want to do is turn the electric field lines. So let me just start over. Let's say we have a surface like this with an area A. And say the electric field lines are crossing the surface at an angle. So before, I had them just going like straight through, but now let's say there's an angle between them. So again, we're still considering these parallel electric field lines, just for simplicity, but we can generalize this later. Answer more general cases later. Okay, so the key phrase I used earlier is we want to measure how many electric field lines are passing through this surface. So let's just look at one of these lines, and we can break it up into components. We have a component in this direction, and a component that's, so we have a component that is perpendicular to the surface, and a component that is parallel or along the surface. And this is the only component that's passing through. And so just like before, we had the electric field times the area. Here we just want this component of the electric field times the area, because this contributes nothing to the flux. This one that's going along the surface contributes nothing. So what we have, let's, I'm going to redraw this again. Sorry about that. Let's start with just our surface here. And what I'm going to do is I'm going to draw what we call a normal line, or a normal vector. Now, never quite understood the reason for this, but in math, normal means perpendicular. Okay, and let's have an electric field crossing through in some random direction. We can say the angle between the electric field and the normal vector, let's say that angle, let's call that theta. Now again, you want to know what angle you're talking about, because there's also an angle here. And so again, it's the angle between the electric field and the normal vector. So now if we break up the electric field, we've got one component parallel to the normal vector. That would be E cosine theta. And we have this perpendicular component, or perpendicular to the normal vector, which would be along the surface. This one would be E sine theta. So yeah, this one's adjacent to the angle, so we use cosine. This one's opposite the angle, we use sine. And so overall, this component is passing through the surface, so the flux would be E cosine theta. So that's just the component of the electric field passing through the surface times the area. So this is a more general case when there's, so let me rewrite it. Let me write it here in kind of its final form. So we have EA cosine theta. Now, it's very important that you know which angle you're talking about. That is the angle between the electric field and the normal vector. And the reason why you have to be careful about that is, let's say that you have an area and you have an electric field going through like this. You know, what angle are you naturally going to think? Well, that. You can see you've got these two lines. There's an angle between them. So if you look at the formula, you might think, okay, there's an angle involved. It must mean this one. No. You have to know that there's a normal vector here. So, yeah, again, like the normal vector probably wouldn't be drawn on the picture if you have like a picture of this surface and the electric field. So you would have to remember that there is you always measure angle with respect to that normal vector. So very easy to kind of get that part wrong. You have to know which angle you're talking about. And then we just define the flux this way. E times A times cosine of theta. Now again, this is still a bit of a special case, because what if the electric field is not constant? So it could vary in either magnitude or direction. Well, that would complicate things a bit. But again, that's a very real problem. Let me give you an example. Let's go back to our point charge, where we have our electric field lines that look like this. We'll just draw it on this side because that's all that matters. And we're going to put our surface here. What if we put a surface like this? And we want to know the flux through this surface. Well, this would be a pretty complicated problem, because the electric field is different magnitude. Like if you want to know the magnitude of the electric field at this point, it would depend on the distance from the charge to that point. That'll be different. The electric field has a different magnitude at these 2 points, and the direction is different as well. This one points in that direction, At one point, like all the magnitudes and directions are different along the surface. And I should point out the surface is actually, perpendicular to the board. So you'd also have to consider, like if we look at it from a different perspective, if this is our surface, we have these electric field lines coming out. They're pointing like radially outward from some point behind the board. So again, fairly difficult problem. Now in theory, we could do this. The idea, let's say this is our surface, and we have these kind of vectors coming out in all directions, and they have different magnitudes at different points. The basic idea, what we would do is we'd break our surface into pieces. Now let's say we break it up into small pieces, where the pieces are small enough so that if we just look at one of these pieces at random, we can say like in this small region, the electric field lines are basically parallel and the same magnitude. And so we can calculate the flux through this piece, and then this piece, the magnitude might be different and it might be pointing in a different direction, but they're still, constant enough in that region. So we can calculate the flux through each of these pieces individually and then just add it up over the entire surface. We also have to consider, what if we had a curved surface? Well, again, if you break it up into small enough pieces, those pieces are going to be flat. Just like the surface of the Earth appears flat if you just look at a small area. The Earth is big enough that has such a large radius that if you look at a small section, it's going to be mostly flat. It would be difficult to detect the curvature. So, again, in theory, what you do, if you have like a curved surface or a non-constant electric field, you just break your surface up into pieces. And then where you can use this formula over any piece, where the piece is flat, the electric field line is constant in magnitude and direction over that piece, and then just add it all up. Add up the flux through each of those individual pieces. Now, the actual process for doing that, again, it's not going to give you an exact answer because this is an approximation. Like maybe the electric field does vary slightly in that region, and you can improve this by making these pieces smaller and smaller. And there's the process of just breaking things up into pieces and adding them up. That can be done exactly using calculus. It's a process called integration. We don't do that in this class, so we just look at the basic concept behind it. Okay, so there's one more thing I want to say about flux. Now, I'll leave this picture up. So, here, I'll just redraw. Say we have a surface here. And we have a normal vector, which I drew this way. Well, what direction should we draw the normal vector? What if we drew the normal vector going the other way? Could we do that? And well, of course, how can we pick one direction or the other? So when it comes to the flux, I'm actually going to draw two cases. Let's say we have an identical surface, except we just draw the normal vector in a different direction. And let's say we have a constant electric field in this region. So we have two surfaces, constant electric field. So this is the electric field, we'll say. And, let's talk about units as well. So the unit for flux, remember the electric field is, newtons over coulombs. So we have newtons times meters squared over coulombs. That would be the units for flux. Okay. So let's just say, for example, that the flux through this surface, I'll just make up a number. Let's say it was 27 Newton meters squared per coulomb. Those are like the basic SI units. Okay, and this is a positive flux because the electric field lines and the normal vector are pointing in the same direction. Now here, the electric field line and the normal vector are in the opposite direction. And so here the flux would be minus 27 Newton meters squared per coulomb. However, what I'm saying is that the flux through each of these surfaces is the same. We're just describing them differently. Here we're saying we have a flux of 27 Newton meters squared per coulomb to the right. And here we're saying we have a flux of minus 27 Newton meters squared per coulomb to the left. It's like saying if I stand here, I could go, say, 2 meters to the right or negative 2 meters to the left. I'm going to end up at the same place. So you're free to pick the direction of your normal vector either way. Just like you have a positive flux, if they line up, negative flux goes the other way. However, there is something, this is one of those rare cases where there's a choice, and basically everyone in math and physics just agrees with this. If you have a closed surface, so let's say we have some random surface, and let's say it's closed, so I'm going to draw it like this, just to try to give it this three-dimensional look. And so a normal vector, basically we have a closed region, so there's an inside and an outside. And everyone just agrees if you have a situation like that, the normal vector, draw it so it always points outwards. Again, you could have just as well say draw it so the normal vector points inwards, but no one does that. It's rare that, there's two valid options, but everyone just agrees to do it the same way. So, bonus, that actually happened. Usually when there's two possible ways to do it, and, one isn't really any better than the other, there's always debates about the correct way to do it or the better way to do it. But no, here, I've never seen anyone do it differently. So, we can just say we're always going to do it this way. For a closed surface, the normal vector points outwards. And that's going to be relevant for what we're going to talk about next. Next, we're going to talk about something called Goss's law. So again, right now we just defined flux. We have no idea what it's good for. But the next topic we're going to talk about is Goss's law, where we're going to learn why this is such a useful concept. But that'll be a separate video. So I'm going to stop this one here.